Hey, hello everyone. So I'm going to present this paper called Bootstrap Your Own Latent. It's a new approach to self-supervised learning. So this paper, it's self-supervised learning because it learns the representation um, for classification tasks like image classification. So first it will learn the representation of the images in an unsupervised way, meaning you don't need any label to learn the representation of your dataset. So it will learn that using, they have two networks called online network and a target network. And at that time, it was published in 2020 and it came from DeepMind. So, and they did a lot of work on this paper. They have a bunch of authors on this paper. So it's a really good paper and it's a significant contribution in semi-supervised learning. And it achieved a state-of-the-art performance back then in 2020, which was 74.3% top one accuracy on ImageNet using a ResNet 50. And using a larger ResNet, they achieved 79.6% accuracy. So let's get into this paper. Here in figure one, you can see a performance comparison between fully supervised learning and their method, where their method only used a linear evaluation, where they froze all the parameters and they had a small MLP, and you can actually see that it achieved the performance very close to supervised learning. And before this paper, BYOL, there was another representation learning, which is called Sinclair. So Sinclair was a good contribution back then in 2020, which came just a couple months before this paper. And this paper also does a lot of comparison between Sinclair and this paper. Sinclair is also from DeepMind. So the problem with Sinclair is very expensive because you need positive and negative pair of augmented images to learn the representation, which took a lot of computational power. So in this paper, they didn't need those positive negative pair. You can have same image and learn the representation. That's why it saves a lot of computation. It's still expensive, but it's a lot better than Sinclair. And you can see also performance-wise, it's much better than Sinclair. Okay, so let's see what they did. So they used a linear representation, what I just showed in the figure one. And yeah, so their contributions are they use this supervised, semi-supervised learning, and they showed that you need a very big batch size in this method because batch size is very important. And they use 2048 batch size, which takes a lot of GPU power uh, to get your full performance, full potential of this paper. And you have some image augmentation here, which were motivated from the paper Sinclair. So you have the same augmentation that they used in the earlier research Sinclair. So I'm not going to talk about recent paper. Let's get into the methodology. So let me show you the Sinclair architecture, the BYOL architecture first. So you have an input image and you do two augmentation. So this is your augmentation one and this is augmentation two. In augmentation one, you have like a weak augmentation, and in augmentation two, you have a strong augmentation. So you can think of this as like a random prop or random flip. And then here you can think of augmentation like auto augment, where you have a lot of color distortion, also with random crop and random rotation. And then you pass it through an encoder. So in their research they did with ResNet 50, and then it goes through a projection layer, which is actually an MLP, multi-layered perception network. And then you have another same MLP, which is your prediction layer. So this network, Y theta, they are calling it online network, and this is the target network. So these two networks are identical, this is identical, and then in your prediction layer, you get an output, which is the dimension would be 256, and the input dimension is 4096, I believe. So you have one output here in the online network, another output in the target network. And then you learn the representation using a mean square error loss. So you don't need a level, you can just learn the mean square error loss between them. And then after you get the mean square error loss, you update your online network through backpropagation. But you don't update the target network through backpropagation. You see this sign here, this is called this SG, it is a top gradient. So backpropagation doesn't uh, flow through this network, but you update this network using this equation, which is exponential moving average. So every time you update your online network, this network gets updated like 1% of this network. So this network would update faster, but your target network would update slowly. So if you want to learn how that works, you can look at the math in more details by using this term exponential moving average. You can see that is used a lot in regression or other statistical models, but I'm not gonna go into that. And this
Excuse
is
me,
the, yeah,
is it a back propagation or
uh, the exponential moving average.
yeah?
So how it works is you have your weights of your original model, and you take that and you add another weight function and like a scale function, and
Okay.
only update your this network. So this network parameter is theta, and your other network, this
Okay.
network is
Okay.
theta,
Yeah,
your
yeah.
this network is this, and you only
And
update like
the
1%.
initialization of the both models are the same or they are
You can
randomly
same, or you
initialized?
can have random initial, it doesn't matter. But
Okay.
once you update this network would be updated like 1% each time. So it
Yeah.
will be very
Okay.
slow, but it would be fast. Yeah. And this is the loss function, which is like L2 loss, and then you have an optimizer to update. Yeah, just like regular neural network. And here they talked about why the network works. So I'm not gonna go into the math, but you can see, since we have this image and then you pass it to network, it the same you try to learn the representation of the same image, and that's how your network knows every image and their inherent latent representation. So that's why it works when you have a supervised task and you don't need a lot of data. So let's talk about their implementation details. So you can see the image size was 224 into 224, and you have augmentation from Sinclair. Here, I need to mention that the image size is very important. Like if you reduce the dimension, your accuracy would drop a lot. So don't use image dimension less than this. And then you have a network architecture of ResNet 50. You can go deeper, and that would improve your accuracy, but that's also going to take a lot of computational power. And your this is the feature dimension of your multi-layer perception network. It was 2048. Yeah, I think that's um output size is 4096 followed by 256. I don't remember exactly what this is, but it's in the network architecture. It's just like different layer size. So and then in optimizer you have a large optimizer, which is like it's basically you when you have a lot of big batch size, you need this optimizer. It takes a lot of computation, and best size is 4096, and they used 512 cloud TPUs. So that's a lot of computational power, which is very hard for us to implement. And it took 8 hours to, I guess, to do one training. The training takes 8 hours on this many TPUs. Yeah.
So I have a question.
Yep.
So did they like try to train the model with a different optimizer, like an atom optimizer and a smaller
They did not,
batch size?
because they did not in their research, because they are trying to get very high accuracy, like they are trying to target state of the art performance. But I have done that with a different optimizer and smaller batch size. That's gonna hurt your accuracy, but it would work. You would still get good accuracy than transfer learning. I'm gonna show the code after I present this paper, but you can do it. You can modify the code and have a smaller architecture so that you can use on your GPU, but it's gonna hurt your accuracy.
Thank you.
Yeah, and they did this, they evaluated on ImageNet dataset. So that it had like 1,000 classes. And these are the output from their paper where I marked Sinclair, which was much like a good accomplishment back then. And then after that, this paper came. So we see that BYOL improves a lot over Sinclair. The accuracy is almost like 5% improvement. That's a big improvement here. And it has less parameters than Sinclair, and it takes a lot less training time. So this is the highest accuracy they got on ResNet 50, and they tried with different other architecture which are much deeper, and they got even 5% more improvement on that. And what this? Oh, they also did their training on 1% of the training data. So this model is trained on only like you first take all the data, you learn the representation, and then use only 1% supervised level data to train your network, and it achieves good accuracy on that. So if you have like a data set where you have only 1% level data or 10% level data, you can take all your data, learn the representation, and then just use the few level data and get good accuracy using this BYOL. So it's on that, and then they showed how it also works on transfer learning, and they showed in most cases their method works the best with transfer learning, and they also showed their accuracy on vision tests. So yeah, I'm not gonna go into details of that. And what I like about this paper is they did a lot of experiments here. Like they basically covered almost everything, and even in their appendix, there are so many details in this paper. Like I can fathom how much experiment they did just to finish this paper, but it's a lot here. And there is another important factor here is the batch size. So batch size is important for this paper, and they showed like if you have a batch size of 4096, it gets the best performance. But I guess you need at least 2048 to have the minimum performance, like the optimum performance. And if you go lower than that, it's gonna hurt your accuracy. And you see this blue line, it's on SimClear. So they showed that SimClear was more sensitive on the batch size, that their method is less sensitive. So even if you reduce the batch size, you are still gonna get better accuracy than SimClear. And this is on the image augmentation. So SimClear was also very sensitive to augmentation. So if you don't follow their augmentation, it's gonna reduce your performance. But here it's gonna reduce, but not as much as SimClear. And then what?
Sorry, can
Oh,
you go to the augmentation part again?
yes.
So do they did all the augmentations like because it doesn't seem to be an order wise.
So Sinclair had like combination of different augmentation, like you do color jitter, random crop, random things, like all you combine all this together, and that's like one augmentation. That's they call hard augmentation. So you have like first you do some color random crop, then you do color jitter and auto augment. All these things combined together is your own augmentation. So what they did here, they removed one each augmentation one time in some ablation study, and then they showed how that's gonna affect your performance. Yeah, so everything together is the best, but if you start removing one by one, it's gonna decrease that way. Yeah, and this is the parameter for the moving average, where you see every time it was they used um, some of the parameter to update the network, but yeah, when I implemented, I used their parameters, so I didn't pay much attention into this. So it's just the parameter for moving average, everything. You can find this in their code. And what do we have next? Yeah, so that's mostly about this paper. This paper covers a lot of the ground, and they improved. They got the state of the art performance back then. I think after this paper, meta pseudo level came and pushed the accuracy a bit further. But before that, this was the state of the art. And yeah, they used 30% less parameters to achieve this performance. So it's much faster than Sinclair, and in their abstract, they covered a lot of the things that they use in their architecture, which is this is their algorithm, but it basically has everything that I just explained. So I'm not gonna go into that. And you can find the image augmentation in here, how they did the augmentation, which is same as Sinclair. And this is the percentage of training data they used and found different performance. So when you use more data, the accuracy is gonna get better. But even if you have less data, you can still get better accuracy than other supervised learning or simpler. Yeah, so I guess that's mostly it. And probably have something. Yeah, if you use a deeper architecture, it's going to improve your accuracy for sure. And I wanted to show one last thing, which is the architecture. Yeah, they have a lot of things here. This is the batch effect of batch size. So yeah, if you have more batch size, you can have better performance. And I guess I just want to show one last thing, which is the architecture that they have a cool picture here. So this is the input, which is like an image, and this is a weak augmentation, this is a strong augmentation, hard augmentation, and they have a ResNet, and then they have a so this is the image embedding, and then you have two identical MLP, which are like one is called projection layer, another has prediction, and then this is the target network, which has like one MLP, and then you take the loss and you do backpropagation to update the network, and you update target network with exponential moving average. So yeah, this is about this paper, and I'm gonna show the code, which is on my GitHub. It's a smaller implementation. Unfortunately, this is not on the main branch. This is on this branch called Torch. So here, this code called BYOL PyTorch. This is the original code that I took from their implementation. The code is very simple to read, and I think their paper is very well written. It's not very hard to read. So this has all the steps in that they used in their method. So I'm not gonna go into that. I'm gonna show this BIOL unsup. This is the unsupervised representation learning and this code. So what you do is you take the network from the other code, which is BIOL. So it comes from the other BIOL PyTorch code. So that's the class of the network that you are gonna take and learn the representation. So here I used the image size 256, and then I used a different optimizer, which is Adam optimizer, and then this class learner, which is the BIOL learner, where you pass your ResNet network, and in this case I had ResNet 18 because I couldn't afford ResNet 50; it gets very expensive. So I modified the network, I modified the learning rate and the image size, and the batch size was 128 for me because I couldn't do more than that on my 4090 Ti and 90 TPU. So yeah, it gets very expensive. I think the whole thing takes 8 hours, I guess, to train this network to learn the representation. So yeah, I did for 50 epoch. You should have a lot more epoch than that, but I did 50 epoch and I learned the representation. And then what I did in the end is I saved the ResNet in the end. And I also had a different optimizer for my ResNet. So I saved like I had two optimizer, one for the learner network, one for my ResNet, and I saved the ResNet to do my supervised learning in the end. So this code is for the supervised learning, which is just the regular supervised learning, nothing fancy here. But what I did is I loaded the saved model from the representation learning model from the BIOL, and then I loaded this network here and did the regular supervised learning, which takes only 30 minutes to learn. And what I found here, it achieves better accuracy than faster learning. Because and one more thing is when you are doing your unsupervised learning here, if you my pretrained was false because I wanted to have a fair comparison, but if you use a pre-trained network, so if you make it true, it's gonna achieve even better accuracy. Yeah, so yeah, that's mostly about it. That's mostly about this paper. Well, do you have any question, Mo?
Oh, no, I'm good.
Okay, yeah, so thank you so much. All
Thank
right,
you.
bye bye.